Hi everyone. Good afternoon. My name is Binghao Huang, and I'm glad to be here. And thank you community's effort for organizing this workshop. And yeah, let me have a brief introduction. And I'm currently the third-year PhD student at Columbia University, and I'm working. My research focus mainly working on robot learning, Dexterous manipulation, and multimodal perception. To be specifically, it's vision and touch. And yeah, today my topic is learning with scalable tactile skin for fine-grained manipulation. Yeah, it's a little bit different from the abstract topic, but I just add a new word learning. So then let's getting started. So here is an overview of today's talk. We will discuss about our unique tactile hardware and how we design it through first version to the second version and how we gradually adapt this kind of technology to the robot learning domain and meet the requirement for some CS people or some people without any hardware background. And the second point is that we know vision and touch are very distinct in their nature because vision can provide very global information, but touch is very local. So how we use these two different modalities and how we make the policy to the condition on both of modalities could be another important topic. And then the third part, I will discuss about my recent effort on how to scale up tactile data. So we can see in the first video, we built something and then we take it out to the lab and collect in the wild tactile data. And in the second video, is how we scale data in the simulation. And yeah, we build a tactile simulation and we will discuss it later in details. Okay, now let's get started with tactile hardware. So I think some people may be familiar with this tactile glove, and I think all the stories came from this tactile glove. And this glove currently is collected by the MIT Museum collection, and my professor Yunzhu has contributed to this glove when it's published to Nature sometimes. So at that time, people use this tactile glove do some screen crafting and hand pose detection. But currently, I have a question is that can we introduce this technology to the robotics, especially for the robot learning domain? Then we will have some following questions. Can we mount it to the robot any effector? That's a simple question, but I think it's a very important question. Because for this kind of hand, the fabrication time is very long. We see at the first time, it takes me about 6 hours to make a simple square pieces. So that actually took a lot of time effort. And also the cable management. We see here a lot of cables and it's very messy. So I think these cables are not ideal for the robot any effector because you need to let your arm to move very freely. So it will help you to do some dexterous manipulation. And also for the reproducibility, even though this hand is open source, but it's still hard to replicate. Some people may know the Professor Yue Luo. She is now like a assistant professor in University of Washington. And when she first joined their lab and tried to reproduce this hand, it took her about 1 year to fully recover the original performance. So we find that even though it's open source, it's still hard to replicate. And the second question is, because this is a resistive material, it can only give you the normal information, so normal force information. So the question is a normal force array enough? Because in the daily life, we did a lot of tasks that sometimes need a shear force. So if there is no shear cruise, can we extract some useful information for the manipulation task? Okay, let's take these two questions in the mind and listen the following talks. Okay, now let's getting started from our tactile hardware. So this is the principle of our sensor, and I built this during my first year of my PhD, and the name is FlexiTac. We recently gave it a name. Previously, we didn't have a name. So the principle is very easy. The key material is this black mat. It's like piezo-resistive material. When you press it, the resistance of this material will change. So what we want to do is that read the resistance map of this black material. So what we do is put a lot of like electrons in the map. So it's a sandwich structure. In the top, there is a horizontal electrons, and in the bottom, there is vertical electrons. And then each intersection of the electrons will be the sensing unit. And then here is the visualization of our tactile sensing. We design a PCB board to read out the sensors. You can see we visualize the sensor in the background screen. It's very sensitive, and the film is very thin. It's no more 1 millimeter. So our goal is to make it accessible, low cost, and robust. Because nowadays, more and more people involved into the robotics domain, and some people do not have like hardware experience. So if we make it accessible to like different part of people, people from different domain, I think that could contribute a lot to the community. Especially previously, this kind of material, this kind of sensor is mainly used in the like material science lab, or like people who did like human computer interaction. Okay, here is an interesting demo. I like this demo very much because we use real egg. So that means this object is very fragile. So and then I will click this egg. So that's a real egg. So that means our robots have the ability to deal with fragile object. And another feature is that we can see here. So the robot needs to put this egg in the middle of two eggs. So if your sensor is not thin enough, that will be hard. For example, if you use Josite, you definitely will put the other two eggs outside the platform. So that's why we want direct say is like small sensor. Yeah. So our sensor is very thin, flexible, and also very sensitive.
For next time, the robot should crack the egg.
No, we can.
Yeah. Oh, I see. Sorry.
Okay. Then, so our goal is to make this tactile sensor accessible to everyone. So we open source the tutorial. I think we open sourced it last year, and we also provide a lot of reproduction resources. So the fabrication time currently, we can reduce it to 30 minutes, and the price of each pieces is $5, and it can be even lower if you make many sensors. And also, I choose accessible material. That means all the material you can bought from Amazon or like very commercial like website, and the fabrication. The fabrication steps, I also optimize it a little bit. It will be very simple. So my claim is that if you could make a sandwich at your home, you could definitely make this sensor at the lab. Yeah. Okay. Then I meet Wunda at ISS, and he mentioned that, oh, hey, Binghao, I definitely can make sandwich at home, but I still can not make this sensor. Because yeah, you still need some like manual work to align the orthogonal lines. Some people maybe do not have much hardware experience. That will be a little bit hard. So we continue improve it to the next version. This is using flexible PCB. So it's more like more industrial product. Like I designed this like top PCB and the bottom PCB as the orthogonal electrons. So that will be much easier. This is a sketch of this design. So all of the like yellow part is designed with flexible PCB, and currently the fabrication time is only 2 minutes. It's just you simply stick these 3 layers together. That will be super fast. And also the price will be much lower because if you made a lot of flexible PCB, the price you can directly get from the PCB factory is about 1.36 per piece. So, and it's also very easy to customize the flexible PCB and we take the benefit from the currently industrial PCB factory because the manufacturing and the shipping will less than 1 week. So to have a like better understanding, it's more like a simple sandwich. Yeah, so it's still a sandwich, but it's much simpler. And yeah, this version will be much robust as previous one because we use flexible PCB to align this conductive thread. That means the consistency will be improved and the distance between the conductive thread will be fixed. And we will also mount this sensor to the robo end effector. This is the task that we want to fetch the water from this cup. And there is small difference when you press this dropper will be recorded by the tactile sensor. But even though if you put the no, this is a calibration. Yeah, but we have a task in a project that do this kind of task autonomously. Here is try to show the small difference when you press this dripper. Yeah. So I think this kind of like a small force difference can be captured by the sensor, and this is definitely can meet our requirement to do the most cases of the like fine-grained manipulation. Okay. So let's have another comparison about different sensors. So the question is why we use FlexiTac, because currently we have a lot of commercial sensors, and why we still need to like do it by ourselves, like DIY this kind of sensors. Why not directly bought the sensor from the company? I think the basic idea is that we definitely could bought other sensors, but if we want make it to meet our requirement, sometimes we need to customize. So it's always there are a lot of trade-off. So let's look at it in details. So for the optical based sensor, I think this sensor geosite is like most commonly used in current robot learning domain, and it can give you the high spatial resolution, and it could also leverage the shear and texture clues. But the major problem for this sensor is a little bit bulky. At least the sensor should be thicker than the camera's focal length. And also, it's very hard to customize. You can see the second figure and third figure. So I talked with the author of these 2 papers, and they mentioned that they put a lot of effort to customize this geo to the robo end effector. Yeah, so the customization of geosite is one of the problem. And then magnetic-based tactile sensor. So this kind of sensor can also give you the shear sensing, and it's very easy to shape. For example, you could easily shape this blue part, and you will get the different shapes in sensor. But this sensor could also have some problems, like the noise of the sensor is very serious because it's magnetic-based tactile sensor, and sometimes it will be influenced by the other magnetic field. And also the resolution cannot be higher because 2 magnetic components cannot be put too close to each other. That's also the point. And the major point for this is if, like, for example, if some people said, oh, even though it has noise, I could apply some algorithm to like denoise or make the signals useful. But I think one of the important part is that this kind of sensor is relatively hard to access because you need to find the magnetized elastomer. That is very hard to make. It's usually made by some material science lab. You need to buy like several different material and mix them together, and then do some blah blah step, and then you will get this magnetized elastomer. So usually this step is very hard to access, and sometimes it's very hard to control it to be very consistent. Okay, then let's see our flexi tag. So I mentioned here, there's no shear force. I think that's a major limitation. But except this part, we can see it has other benefit. The first is it's flexible and compliant. So it will be a best suit for the soft gripper. So people now like soft gripper.
Oh, sorry, I want you to continue, but
Okay.
Yeah, I'll ask after you're finished.
Okay.
Sorry.
So people like soft gripper because it's flexible and can provide additional compliance. If you want to put optical sensor on the soft gripper, you need a lot of engineering efforts. But for this kind of sensor, you could simply stick it to the surface of the gripper. And also it has good resolution. So I mean, good resolution is that it's not as high as camera. It's very hard. It's almost impossible. But I think the 2 millimeters resolution is enough for some for most cases of manipulation. For example, for the human fingers resolution, it's like there is a test in cognitive science. They use like 2 points to press the human's skin and let the human to distinguish different it's 2 points or the 1 point. So there is a minimal distance. If these 2 points are too close to each other, the human cannot distinguish. So for the human's fingertip, human cannot distinguish the distance between 2 millimeters. So that's why I think 2 millimeter is a good resolution for the robot and effective. And also it's very thin, and I definitely should like how thin tactile sensor can help. Also, it's very easy to customize. Yes. Oh, you can.
Sorry, I didn't mean to interrupt.
Okay.
So I noticed you put the sensor on the thin ray gripper, which is compliant, and you mentioned like you can put it on the soft gripper. But if it bends, is there like you get interference like in the measurement because of the bending?
Yeah, there is like interference during the bending, but you can eliminate it. And I think in our sensor, the problem is not very serious. We can see the later videos to check if the bending will have a lot of noise.
You feel so you have to do some post process filtering, like because of the thin ray, like complying and then entering into the force measurement.
Oh, usually we didn't do like a post processing for that. I think the signal is clean enough. We can see later videos.
Yeah. Sorry. One more question.
Okay.
Is there a maximum curvature of like how far can you like bend the film? Like, will it like damage the components if you put it on over like a corner?
I see. I bring this sensor to here, and you can feel it later after the talk. And I think usually when you bend the sensor in like this angle, I think it's always fine. Yeah.
Okay.
Yeah.
Thank you.
But sometimes when you bend it, it's actually when you press it, the sensor, the signal will be a little bit different. Yeah. Okay. Yeah, here I just want to say that we show the real-time tactile feedback in the background screen for every videos in our project website. So what you see in the project website is what your sensor will get. So it's like, I know some people will like pick some better visualization on the website, but we show the visualization in every videos. I think it's very reliable. Okay. Let's continue. So I'm for comparison, I'm not going to like downplay like downplay the optical-based sensor. Is my basic takeaway here is that I find that optical delivers micro precision. That means we can see here, I put 3 pictures. We find this optical sensor can give you very detailed information, especially for the defeat inspection. I have talked with some professor in aerospace and mechanical engineering. They mentioned they will do some like metal detection for the airplanes. So that kind of defeat detection is like if you're using geosites, that will be the best solution. But for this flexi-tag sensor, we find that flexi-tag it can scale cross robots and tasks. It can help you to scale the robot platform better. So here you can see the second picture. This is taken by Google DeepMind. They put a lot of like Aloha robots in their like workspace. So I think the basic idea is similar for our sensor. It can help you to easy to install this sensor to your robot any factor. So my takeaway is that consider both hardware and software together to help you to build a better robot. So there must be some trade-off, but this trade-off, and we could adjust them and choose the better sensor we want. So just to be a like simple comparison is that we know the Franca robot and the Aloha robot. We definitely know Franca robot has a better accuracy than Aloha robot, but it's still in past 2 years, Aloha has increasing popular in the domain. Why is those kind of low-cost robot and without much accuracy can still get people's attention? It has some benefit is scalability. So I think this comparison is similar for tactile sensor setting. So that's why I would try to make this sensor accessible and scalable for the robot system. There's a question in the channel. If you need to replace the sensor, do you recalibrate? Do you need to let me check. Oh, hold on. Okay, the question is that if we want to replace the sensor, do we need to recalibrate? So the question is no. It's we have did the experiment asked by reviewer. They asked if we collect the data with a pair of sensor, and if we change the sensor, do we need to recollect the data? So that can definitely show the consistency of the sensor. So we did additional experiment for that. We find that we do not need to recollect the data. We could directly replace the data. I think the key point here is that if we normalize those kind of simple normal array from 0 to 1, so the distribution will be similar. So that's why we may not to like recalibrate the sensor after we replace it. Okay. Yeah, here is some video demos that after we release the tutorial in just a month, like people from academia and industry have already reproduced our sensor and get the video back to us. Then after a year, I think it's within a year. So we released the sensor in last year's November, and currently people publish paper using our flexi-tag sensor. And I like this video very much. They stick our sensor to a 3-finger Dexterous hand and grasp a light bulb and install the light bulb to the base. So I think this task is pretty hard. Yeah, but it's enough. So they also this video is very fancy that they also added geosite at the top. I don't know how they render this geosite image, but it doesn't show any clear signals. Yeah, maybe there is some signal, but it's not very obvious. And yeah, and in the right, there is our sensor used and extended by the university and the industrial labs. Okay. Yeah, let's continue. So let's back to the question 1. So can we mount it to robot any effector? Yes, definitely we can. So it's even have a better fit. So any questions so far? Okay.
Also, what's the force resolution of the sensor?
Oh, wait, sorry. What's the force resolution?
Yeah. Like, what's the, for example, like the lightest force that you detect?
Oh, I see. Yeah, the lightest force we can detect is about like 0.25, 0.25. Yeah, that can depend because sometimes if you apply a very like low force, that will have a lot of like noise. So it's a trade-off between the noise level and the sensitivity. Yeah, so sometimes we will set a higher threshold that will lower noise. Yeah.
Sorry, drift and also like lifetime. I know that like regular FSRs, they have drift over time and also like people live longer, it may kind of like jumble or something.
Oh, you mean it will like have
Yeah.
a upper limit?
Yeah, the curvature of the like force versus distance and rest changes. The slope changes the more you.
Yeah. So you mean that the piezoresistive material has like features that the force related to reading is not linear, it's
Yeah.
non-linear. So yeah, usually when we do the calibration, we will like find the minimal force and find the max force and choose the linear part.
But at some point,
Yeah.
it like just dies, right? Like at some point, at least from like some personal experience. Like,
Yeah, I
they
know
start
that.
to, like not,
Uh-huh.
I guess like how long do you kind of expect the
I see. Yeah, for first of we haven't have like long time using for our second version tactile sensor, but for the first versions of our tactile sensor, I think last year I made four sensors at NVIDIA and I leave the NVIDIA and they have like no tech to change the sensor and they use it for the whole year. It all works. So that's the longest time we have used the sensor. So compared to the geosite, sometimes you need to replace the gel on the top of geosite. It's about like 1 month. That will be a relatively short time, but at least our sensor can work more than 1 year.
So I see a lot of these videos with the material is flat, right? You have flat defectors. Do you foresee any significant limitations to implement this in a sort of spherical form factor? I can imagine on a fingertip, like.
Oh, it's like a sphere shape.
Yeah.
Yeah. That's also the problem. I think that's related to the like manufacturer like technique. It's like once you have like virtual manufacturer tech, you could like shape it to different shapes. And for current sensor, if you simply put it to the curved surface, it can also work well. Yeah, it's just that you need to do some like at first at the initial of the sensor reading, you need to read some initial signals and cut that initial signals of your output signals. Yeah, so basically this type of sensor can be applied to like curvature and sphere shapes. That will be easy. Yeah.
How small can you cut the pouches of this sensor?
You mean the sensor unit? What's the size of the sensor unit?
Yeah, I was thinking about it, because if you curve it, you can get like cylinders, that makes sense. It's flat material, but if you want like to approximate a sphere, right, you need either really small
Oh,
pouches,
I see.
right?
We haven't tested it, but if the surface is like it's like a too curved, it will be hard. Yeah. Okay. Yeah. Now let's look at the second question. Is a normal force array enough? Let's take the second question in the mind and listen the following work. So I think this question can be translated to another question: is that what we expect touch to add to your policy? So my answer is that the contact and interaction clues and the shape and the state clues. Okay, let's look details about this work. So this work is, I have been done this work during my first year of PhD. It's 3D tech learning fine grained manipulation with visual tactile sensing. So in the left, we see a real world policy rollout. The robot need to, let's replay the video. So the robot need to grasp this hex key while it didn't play. Okay, the robot need to grasp this hex key and then reorient the hex key. Because current pose is not ideal for the insertion. And then perform the insertion. Yeah, that shows that touch can give you some kind of objects orientation information. And also in the left, that shows the real-time observation is composed by the vision and the tactile. We will see how we compose this representation. So here is our process. We first get a multi-view RGBD cameras and get this point cloud, and then we will downsample the point cloud to lower resolution. And then we can find some like edge or some features of objects will not be very obvious, especially for this hex key. We also have tactile. So we have tactile readings. We also have robo perception. And then we could use robo perception to calculate the tactile position in 3D space. After we get these tactile points, we will then merge these tactile points with vision points together, and then we construct this representation. So this will keep the tactile contact points and the vision has the spatial colorations. It will help it's more like add some prior to the representation. And then we will feed this representation to the point net and get some feature and feed to the diffusion policy and condition on 2 time steps to output the action sequence. Any question? Yeah.
Yeah.
Okay.
Quick petty question.
Okay. Okay.
Why 3D? Like diffusion policy works great with images, than just images plus tactile without any point clouds and pose estimation, alignment.
Yeah, that's a good point. We find there is a paper called 3D diffusion policy. We also find the similar results that if you train with point cloud, it will train faster, and it's more. It will require
faster. You mean that you need less demonstration.
Less demonstration and train faster, and also for here, we just want to find a simple solution that fuse the vision and tactile together. So we find the point cloud representation is good to fuse the vision and tactile and helps them to build the spatial relationship. Okay. Yeah, here are some demos. This is another my favorite demo. The robot need to grasp the grip, and it fail, and re-grasp, and put the grip. So why I think this demo is very good is that we can see the robot fail to grasp, but before the robot move out to this bag, the robot will retry to grasp. So without touch, I think this task will be hard to finish. And yeah, I think for the human's motion, when the human grasps something with occlusion, human will also fail. But what's important is that human could re-grasp it. So the second video is it's the same hex key reorientation task, but it's a different hex key. Reorient and perform accurate insertion. So this can show that touch can help to add the in-hand state information, because when the two hands coordinate with each other, there are huge occlusions. You cannot explicitly check the hex key's pose. And also, this is another task that gets my hand to put the egg down, and the robot will re-grasp the egg. That shows that with touch, it's easier for the robot to learn some recovery behavior under occlusions. And the final task, yeah, this type we can see in the background tactile signals. When the two tools interact with each other, the signal will have a slightly change in the screen. But this kind of slightly change will be hard to captured by the vision. So we incorporate this kind of signals, and after the robot interact or coordinate with each with another arm, it can still perform the task by manual coordination.
What's the point cloud we see? There are these reflective materials, very tiny objects. The point cloud was working well, no problem.
The point cloud works not very well, especially for the grip demo, because the grip is very small. Sometimes you want to like, sometimes if your camera is very noisy, the noise will cover the grip's size. So that will make point cloud very hard to distinguish. Yeah. And also you could track this project's website, which show different tasks, point cloud observations. Yeah. Okay. So here is another takeaway for this project is that we put the tactile signal in the background screen that when you collect the demo, the human could see the background screen. That helps the operator to make decision if I need to switch to next stage. So it's more like to build some causal relationship between the touch and the actions. So we find that visual haptic feedback for the human is very important to collect the high quality data. Okay, now we can answer question 2. Is the normal force array enough? Yes, I think in most cases, it can help you to improve your manipulation. So yeah, the spatial relationship between vision and touch could also help. And also we will incorporate history information to the policy learning process. It's like we condition on 3 steps history or 2 steps history. It will kind of implicitly infer the shared information. Okay. Okay.
For the 3D feedback, do you plan or does the operator have tactile feedback?
No, operator do not have haptic feedback. It's actually very hard to build the haptic feedback, but we visualize the tactile.
So can operators see those signals?
Yeah, operator can see the screen and to know, oh, my gripper has already grasped the object. I think that kind of feedback is also very important for the operator. Yeah, it's all like a trade-off. It's like you build a haptic feedback that's definitely better, but you cost a lot. It's very hard to build. Okay.
I see the 3D point cloud works really well with background sensing here. My question is, if it's you work in cluttered environment, like for example, can you just choose the specific items from cluttered object?
I see.
Can you help that?
That's very hard. Yeah, cluster manipulation is always a challenging task. Yeah. Okay, let's continue. So if we're still not satisfied with this performance, for example, like generalization or robustness, especially we for this project, we train on 30 demos. But if you put the object out of distribution, like whether it's vision or touch, it cannot perform very robust. So what we are going to do? Now let's go into the third part, scale up tactile data. So we feel like data is always the key point. So the first way is we will scale it in the real, and the second way is we will scale it in the simulation. So we can see in the last video is the autonomous policy in the real world, and the right is the autonomous policy in the simulation. Let's see how we build this kind of scalability of the tactile data. So we have 2 directions The first is build the scalable tactile in the real world, and the second is in the simulation. Let's look at the real path first. So we built portable devices. This is device you must be familiar with that. It's a Yumi gripper. It's original paper published by Stanford, and we touch our tactile sensor on the top of this gripper. So that also shows that our sensor is very easy to touch to any surface that you want. Okay, then we bring this gripper outside to our lab and collect a lot of data. It's like 2,700 videos and including 43 tasks. And this locations including like university campus and grocery store or the like student makerspace and graduate student lodge. There are a lot of space. So the objects diversity will much more than you only collect data in the lab space. Then what we are going to do with large scale data set? So we just simply do a standard cross attention reconstruction, and we train this, pre-train this vision tactile encoder. So this red arrow is our vision tactile encoder, and then we do a simple task. It's like input the image and input the mask tactile, and this encoder to the reconstruct tactile. Yeah, so this is just verified, so it's not like used to the whole pipeline. And then we will leverage this visual tactile encoder to the downstream task training. We combine it with robot proprioception and let the different policy to condition on like vision and robot proprioception and tactile together, and then we will get a robust policy. Yeah, let's see the workflow. So this paper is recently accepted by NeurIFS. Yeah, this is first we collect data in the wild, and then we train a pre-trained encoder there, and then we recollect downstream task data and fine-tune our encoder on the downstream task. And then we will get this robust policy in the third figure. We can look at again. So the robot grasps the transparent tube from this box and reorient, and the human will reorient it back and reorient back again. But the robot can continue to reorient the transparent tube and do the insertion. So even though with the camera, it's very hard for the vision to distinguish this transparent tube is in which kind of reorientation. But tactile can give you a very explicit signal that's all related to its implicit or the explicit. Okay.
The interpolate dataset has only images and tactile, doesn't have the trajectory of the end effector.
It has. Yeah.
Okay, but you don't use it at pre-training time.
Yeah. We don't use that. Yeah, it's that's
a way to train a policy on this and see if it has any zero shot capabilities.
That will be hard actually. Yeah, we still need like fine tune on the downstream task. Yeah. Okay, so for the real task, we develop portable devices and bring it to outside to the lab to have a quick real data collection. Why I say the quick real data collection is that if you collect data with like some like Aloha system, you need to teleop the robot. That needed like some learning curve for the operator. But if you use this kind of portable gripper, that will be very natural for the operator to collect this kind of data, and it will be much faster to collect a new data. Okay, now let's see the second task. Oh, the time is, that will be, time is very limited, but it's okay, we can talk a little bit longer. So let's see how we scale tactile data in the simulation. So this work is led by Columbia, NVIDIA, and UC San Diego. For this work, we did 2 robot setups, and we will see that in details. So humans rely on touch to do the compact insertion. But if you let the robot to do that, what will happen? So if you train on small amount of real data, for example, previous project, we trained 30 demonstrations. And what will happen? Let's see. So the robot perform the insertion, and it also inserted to accurate pose, but it didn't complete the task because it's just a simple imitation learning. It's like the robot mimics the motion, but it didn't care if the task has been completed. So we're definitely not satisfied with that. I'm not satisfied with a lot of stuff. Yeah. So what I'm going to do here is that I build a GPU parallel tactile simulation. So with that tactile simulation, we could fine-tune the tactile policy in the reinforcement learning, in the simulation with reinforcement learning. And then we transfer the policy back to the real world. And we see here the robot initially not insert very accurate, but it fine-tuned and doing such wiggling behavior and do the insertion.
Maybe a question about this, like for which kind of tasks do you think it's easier to build a simulator, train with RL, transfer, than just, I collect 20 demonstration model?
I see. But we have a lot of limitations on simulation. For example, if you want to do the deformable object, that will be hard.
Yeah.
So I think the rigid objects will be easy to simulate and could do such kind of real to sim to real pipeline. Yeah. Okay.
Did you find any like diverse shape of objects?
Yeah, for this task, we try 5 different assets. We will see that later in videos. Okay, that's our tactile simulation. We built that in SFI, but we all know that SFI's contact model is not good. But this is the calibration, and that is we record the calibration and replay in the simulation. We see there is a close match. Yeah, because it's very obvious at this stage. It's very close match. Okay, so that's how we build that. We first build a black mesh on the top of the gripper, and we could use some package to sample tactile points on this black mesh. And then for each tactile point, we will build a spin damper system between the object. So it's more like we query the object position, object velocity, and the tactile points position and tactile points velocity from the simulator, and then recalculate the penetration between the tactile points and the object. And then we could have this rendering. So it's more like a rendering tool. It's not based on the SFI's internal contact model. So here is the histogram. We see the blue one is the real tactile sensing, and the yellow one is the simulation tactile sensing. It's like we use same calibration trajectory and record the sensing readings and print the frequency of each sensor reading, and we can see, even though they are a little bit different, but I think it's a close match. So the key takeaway here is normal force is easier to simulate. So we know there are a lot of existing simulation for geoscience. If you want to simulate the image, that's pretty hard. Also, you want to simulate the camera image from simulation. It also has a lot of gap from the simulation and the real. So, but the normal force field will be easy to simulate.
I'm kind of confused by the histogram of this graph. Is there, like, are you just saying that the distribution of readings that you get between the real and the sim sensor?
Yeah, it's like, for example, the 0.2 is like for the whole episode, you replay the trajectory, and the frequency of 0.2 appeared in your whole sequence.
All right.
Yeah, that's a histogram.
Are you able to directly? Oh, I guess it's like the same sequence, but they're not perfectly timed.
Yeah, yeah.
So thank you.
Okay. that's how we did the policy training. So let's talk a little bit faster. So the first row is almost the same as my previous work, 3D by tech. And then we build the tactile simulation, and then we could get similar, very similar observation between the sim and the real. Also, we did some data augmentation. We add some noise to the point cloud. So we can see this real point cloud and sim point cloud is very match. And then after we directly transfer the diffusion policy to the simulation, roll out the diffusion policy. It can have a performance drop, but it can still work a little bit. And then we fine tune the diffusion policy with DPPO. It's basically like a diffusion PPO. Yeah. Okay. So the benefit is very obvious. We use 30 demos collected in the real world. For 30 demos, it can you can collect it within 30 minutes. And then we use sparse reward. It can be easy to extend to the new task. So the reason why we use dense reward is I'm lazy. I don't want to do the reward engineering. I think reward engineering is very tough. But as we have the initial motions, we do not need to have to do the reward engineering. So that's why we use sparse reward. And also sparse reward will be easy to extend to a new task. You can see the video. I did this 5 tasks, I think within a week, because it's from same data set and the reward is very easy to define. It's insert or not. If it insert, it output 1, and if not insert, it output 0. So it's very easy to extend to a new task.
You have 30 demos for each of those, or
what?
30 demonstrations for each task, or just for one and then you generalize to others?
Oh, we have 30 demos for each task.
For each task?
Yeah. So it's total 150 tasks.
And how many steps do you fine tune with RLC?
I do not quite remember it, but it will take about 1 day to fine tune the simulation.
See.
Yeah.
Like since the reward is so sparse, why not doing directly fine tuning in the real world?
That's another good point, because real world IO is usually cost a lot, cost on robots and other stuff. Yeah. Now I still believe the simulation can help a lot. Yeah. Okay. That's another robot setup. This is NVIDIA's Rami robot, and I built this sensor last year, and it can last for now. Yeah. So we do another robot setup that could also show that our pipeline could be easy to extend a new task and a new robot setup. Yeah. I think the time is limited. Maybe comparison. Okay, we still have some time. So
Binghao, in these tasks, I mean, I understand it in the other ones with the glass objects, etc., where there is perception difficulty, and also in the ones that you really use force. But here, any compliant control would probably solve it without that, right?
I see. I think for here, what we want to do is using reinforcement learning to add more this kind of wiggling motion to insert the objects. Yeah, but sometimes if you develop the compliance control, I think it can prevent the two objects client together, but it may not add some this kind of wiggling motion to finish that.
I agree on that. But you could use the wrist. If you have a wrist sensor for force and torque, you have a sensor here. You could somehow feel.
Oh, I see. Yeah. That also makes sense.
I mean, this is similar to peg and hole, and it's often the strategy it's taken.
I see. Yeah, that also makes sense. But sometimes there will be slipper happen during the manipulation. But if that happen, with the force cannot help. We can see later there is a video. This video. So here we see when this hand grasp it has some slipper happening in here, you see here. In-hand sliding happens. But it can still finish the task. So this kind of in-hand sliding happens. only you could have the
Yeah.
like directly shape information in hand. You can finish the task. And for the pre-train with tactile, so this is no fine tuning. You can consider it a pure diffusion policy. And if it cannot insert at the first step, the task will directly fail. Okay. And this is another comparison between with tactile and without tactile. With tactile, sometimes you could get the insertion directly in a very accurate position. Without tactile, even with fine tuning, you can see the robot will try to fine tune and try to insert. I fine tune in the wrong place, so it still cannot finish the task. Okay. So here is some results, and we can just go through that. The blue line is the tactile curve. It's all happening in the simulation. So we find that with visual tactile representation, the fine tuning can improve the success rate faster. And also in the initial stage, we find the visual tactile policy could have a little bit higher success improve in the initial stage. So the takeaway here, the visual tactile leads to more reliable and robust manipulation. So that's a final takeaway. The final takeaway is for our real to scene to real pipeline. So we first train diffusion policy in real, and we also try to roll out this and get a success rate. And once we transfer it to the simulation, it has a performance drop down. And then we fine tune it to a higher level. And then we transfer it back, it still has a performance drop down. But still, compared to this point and this point, the performance is increased a lot because simulation help. Even though this pipeline is a little bit complex, but it can help. Yeah, so the takeaway here is even though simulation gaps still exist, but fine-tuning helps even more. So that's how we balance this kind of stuff. Yeah, we use simulation to increase local exploration. It's like helps the robot to learn some wiggling motion to do the insertion. Yeah. Okay, so let's back to the hardware. So we guess the answer of question 1, yes, it can feed the gripper even better. And question 2, yes, in most cases. So that means it will be easy to scale up the data. So that's why I do the 2 projects to scale up data in both real and the simulation. Okay. Yeah, that's acknowledgement to all the collaborators and acknowledgement for the universities use my sensors. I think I sent a pair of sensors to Dinesh after the NYC Computer Vision Day. Okay, here are some future work. Yeah, we will like collaborate with Giga Hand's author, and she will come in the next week to hear for talk about her Giga Hand, and we will also collaborate together to provide the ground truth for their contact model. Because even though they can like predict hand motion very accurately, they still need the touch to provide the accurate ground truth for them. So we can see some simple demo. So I put the tactile to the glove, and we can see the edge of the cup. Yeah, but this is like very initial stage. We haven't improved it a lot. Yeah, another like future work is that we currently exist a lot of vision policies. If we do not want to collect a lot of tactile data, we could directly fine-tune the vision policy with tactile and get a like vision policy, get a VLA policy with very fine-grained manipulation. Yeah, that's a very like rough plan. Okay, yeah, that's all for today's talk, I think. Any questions here? I think we're covering
But it's very in part of the work paper, why is still necessary to design angle adjustment context? When the robot is already collecting data from multiple angles during the collection phase. And why the policy is not directly located in research?
I think that's a very good question because during the bimanual coordination, the occlusion is very heavy. So the robot cannot rotate the text key in a very accurate pose. We also see the vision baseline. The robot could do such kind of reorientation motion, but it cannot reorient in a very accurate pose. If the robot cannot reorient very accurate, the following insertion will fail.